Hi, I'm Daniel Rukhovich and I'd like to present our paper for S+SSPR 2020. The title is IterDet, Iterative Scheme for Object Detection in Crowded Environments. First, some words about object detection. A typical object detector maps an image to a set of bounding boxes. Each box is represented as 4 floats, 2 for coordinates of the top left pixel, 1 for width and 1 for height. Example of objects bound in boxes drawn upon an image are shown on the right here. Typical object detector outputs a lot of similar overlapping bounding boxes for each object. So to solve this problem, almost all state-of-the-art detectors utilizes non-maximum suppression at the last step of the inference process. This non-maximum suppression is parameterized by overlapping threshold, which tends to two different cases in terms of number of boxes. First, narrow suppression improves recall, yet keeps duplicates. And wide suppression improves precision, yet loses some overlapping objects. So we see that crowded environments are the most challenging case for non-maximum suppression, since both wide and narrow suppression leads to errors. For non-maximum suppression, higher precision leads to worse recall and vice versa. Why not detecting objects in several iterations? First, we don't need to assure high recall at each iteration and favor precision instead. We might miss the more difficult objects at the first iteration, since these objects can be detected later on. This iterative idea is the base of our method. The full scheme is presented on this slide. Here, the unchanged meta-architecture of an arbitrary detector is marked blue. It contains the backbone network and usually some FPN and head layers. The input of the detector is an image, and outputs 2 bounding boxes on this example. However, the input image contains 4 highly overlapped person instances. We apply 2 modifications. First, we make the detector history aware, and then we predict different sets of objects on each iteration. The proposed modification is marked green. 2 bounding boxes detected on previous iteration are mapped to a history image, and then through a single convolutional layer, it's just summed up with the output of the first backbone layer. Now some more formal details. For a given set of bounding boxes, we define a history as an image of the same size as the input image. In this history, each pixel contains the number of already detected boxes that cover this pixel. We can make a detector history aware if we pass the history along with the image as its inputs. So, given an input image, IterDet produces a set of bounding boxes iteratively. First, the output set is empty, and then for some number of iterations, we create history image from already detected boxes, and then predict a current set of boxes from this image and the history. If the predicted set is empty, we just stop the algorithm. Otherwise, we add all predicted boxes to the output set. So the question here is why not predicting only one object per iteration and don't use non-maximum suppression? Of course, it's possible, but first, it would be inefficient, since inference time is proportional to the number of objects in an image. Second, our experiments demonstrate that 2 iterations are enough to achieve the best accuracy. During training, we randomly split the set of ground truth boxes into 2 subsets, old and new, such that their intersection is empty and their union is the whole set. We force IterDet to predict only new bounding boxes in the following way. The history depends only on old boxes, and the loss depends only on new boxes. Here we briefly cover object detection methods, as our scheme is just a small modification upon any learning-based detectors can be divided into one-stage and two-stage. From these two sets, as an example, for our baselines, we use RetinaNet and faster RCNN. Our implementation is based on PyTorch plus MM detection framework and is available on GitHub. We train our models with default parameters from MM detection, including 8 GPUs with 2 images per each, and HGD optimizer for baseline models, and ADAM optimizer for our IterDet. During training, we use 2 augmentations, it's horizontal flip and rescaling of all images. We compare our method with existing detectors on 4 crowded datasets. First 2 were introduced in the adapters paper and contain small images with extremely overlapped bacilli-like instances. The last 2 datasets are wide-known CrowdHuman and Person with crowded scenes with person instances. Here we demonstrate IterDet against baseline result on the image from CrowdHuman test set with visible body annotations. Objects detected on the first and second iterations are marked as green and yellow respectively. We see that the second iteration brings 9 more correct detections, and which is more important, it covers the extremely overlapped case of 2 persons, which cannot be solved by faster RCNN with non-maximum suppression. On adaptive toy V1 and V2 datasets, IterDet with 2 iterations achieves almost perfect results, breaking 99% of average precision metric. Our main results are for CrowdHuman with full body annotations. Here we compare our method with all existing ones like soft maximum suppression, adaptive NMS, repulsion loss, and PS RCNN. In terms of MMR and average precision metrics, IterDet outperforms all existing methods for both detectors. For wide CrowdHuman datasets with visible body annotations, IterDet also outperforms the baseline in terms of MMR, which is the main metric introduced by the authors of this dataset. For wider person dataset, we also achieve significantly better results in terms of all metrics for both detectors. Here we visualize some results for all datasets. It can be seen that the most overlapped objects are successfully found by IterDet on the second iteration. They are marked yellow here. So, as a conclusion, we present an iterative scheme of object detection designed for crowded environments. It can be applied to both one-stage and two-stage object detectors. On challenging adaptive toy V1 and V2 datasets with multiple overlapping objects, IterDet achieves almost perfect accuracy. Through extensive evaluation on CrowdHuman and wider person benchmarks, we show that the proposed iterative scheme outperforms existing methods when applied to either two-stage or one-stage detector. Thank you.